In this web talk, I show how to use Mplus to do dynamic structural equation modeling, that is DSEM, with cycles. By cycles, I mean circadian rhythms, that is 24-hour cycles such as heart rate, blood pressure, and sleep. In this talk, I focus on the psychological measure of positive affect, which has also been found to show cycles. And I'll also take a look at tiredness and how those two variables relate to each other. In addition to cycles, weekday effects will also be studied, and I'll show you how to look at that. This is joint work with Tiomir Asparahov. It is Webtalk number 7 in the Mplus Webtalk series. It can be seen as a continuation of Webtalk 6, which also focuses on DSEM, uses the same data set, but doesn't get into cycles modeling, although it mentions this possibility towards the end on slides 120 to 121. Webtalk 6 gives an introduction to DSEM and is therefore a good starting point for those who are not familiar with the topic, but it's not necessary to first listen to Webtalk 6. The background for this talk is different from previous talks in that it draws on a paper where you can read more about the details. And actually the structure of the talk is a little different from that of the paper. It's up to you if you want to read the paper first or listen to the talk first. The paper was submitted for publication in February 2024, and 3 months later we have improved the algorithm to the point that we could release Mplus version 8.11 in May. The paper also comes with a supplemental material which shows Mplus inputs, many of which we're going to take a look at and go through here in the talk. And the example, which again is the same as that of Webtalk 6, has to do with modeling of daily cycles and weekday effects for positive affect and tiredness among adolescents 12 to 16. So this is an intensive longitudinal data collection where experience sampling methods have been used. Several measures per day were taken at random time points for 7 days, Tuesday through Monday. And the analysis that described in Webtalk 6, we used the Mplus t-interval option to discretize time using 3-hour bins, as explained in that talk. We have 240 adolescents, and we end up with 56 time points. We're going to look at 7 category positive affect items: relaxed, satisfied, confident, happy, energetic, and excited. And we're going to do an analysis of both the total PA score as well as analyzing the factors behind the PA items. And again, here you have the introduction to DSEM. This web talk includes a prologue and also an epilogue at the end that further motivates the study of cycles. We're going to take a look at the relationship between positive affect and tiredness. So what we're looking at here in the graph is the observations throughout the week, starting on Tuesday and ending with Monday, 7 days later, where we have early morning hours here in the left part of this section of the day and late evening hours over here to the right. And we see that tiredness has a dip, that is your perkier, in the middle of the day and increases to higher tiredness towards the evening. That seems to be the cycle that happens every day. And that's to be expected for tiredness to follow a circadian 24-hour rhythm. That we could capture by this so-called Cosinor model, that's sine-cosine type of function. And we may also wonder if such cycles affect PA. Positive affect here increases towards the middle of the day and then goes down, increase and then down, increase and down. So that positive affect could perhaps also be, that variation can be captured by a circadian type of cycles model. And you may actually ask yourself then, what is the relationship between PA and tiredness? You see that when tiredness is low, positive affect tend to be high, Same thing here. And when tiredness goes up, positive affect goes down. So we see a distinct relationship, opposite cycles feature for the two outcomes. And you may ask yourself, is positive affect just another measure of not being tired? Does positive affect convey something beyond just being tired? So you come to the third question here. Is there a relationship between tiredness and positive affect after accounting for these cycles, after controlling for these circadian 24-hour rhythms? And that's going to be a key topic that we're going to come back to also towards the end of this talk. So turning to slide 4 then, what we're going to focus on in this talk is to a large extent residual relationships between PA and tiredness. And ask ourselves then the question again, is there a relationship between tiredness and PA after accounting for cycles? That is there a residual relationship? And we can draw a simple picture of this. We have positive affect at a certain time point t here, and we have tiredness at the same time point. And we want to see how the cycles at time point t affect the two variables. And we are not interested in the effect of tiredness on PA, but rather we're interested in what's left in tiredness after we've taken out the cycle's influence, that is what is in the residual here. We're interested in how that residual influences the residual or positive affect. So this is the path that we're interested in, and that's a linear regression, which also has a residual. Now the paper and the talk shows that we're using only two cycles, variables. We need not one, but also the second one, can account for these circadian rhythms using the so-called Cosinor model, sine-cosine modeling. Turning to slide 5, what we're going to end up looking at in the epilogue at the very end is a bivariate two-level residual DSEM model with cycles that looks like this. Quite complex, and in line with standard DSEM, what we show here is the outcomes at time point t and time points t minus 1, so we can show directly in the model relationships between them. At the top we have PA, at the bottom we have tiredness. We have a within part of the model, variation across time, and a between part of the model, variation across individuals. So again, what we're looking at here, if we focus on time point t, in this part of the model, we're interested in the residual in tiredness after we've taken care of the cycles, which are represented by x1 and x2. After we've taken cycles into account, what is the residual of tiredness, and how does that residual affect the residual in positive affect, where we've also taken out the cycle's influence? Now this model then complicates the picture even further by having random effects, that is coefficients, regression coefficients that vary across individuals. So we have 7 such coefficients that then become continuous latent variables, 7 more circles on the between level in addition to the random intercept. Now this is a complex model where you certainly should not start the analysis with this kind of a model, but start with the details of the model that we're going to go through step by step. First doing univariate analysis of one variable at a time, and first doing analysis without random effects. And we're going to take them through a series of 5 steps that are outlined in the paper. On slide 6, I show the analysis steps, which I describe in table 1 of the paper. There are 5 steps. Step 1 is trying to find if there are cycles and what they look like and what their duration is. So this is sort of an exploratory step for which cross-classified DSEM is especially useful because it allows for estimation of between time estimates. So time-specific estimates that can describe the cycles. And you can plot then the observed means and these time-specific estimates to take a look at what the cycles, what shape the cycles have. So this is an exploratory step, whereas step 2 then takes the confirmatory step where you fit cycles to a specific Cosinor model. That is a model with a specific shape for the cycles. So it's very much like the exploratory confirmatory steps of factor analysis. And we're going to start step 2 with using fixed cycles coefficients. I'm not a fan of starting off with random effects right away, but I'll try to learn first about the model using fixed coefficients. So that's what I'll show you. And we're going to take a look at cross-classified DSEM again, like in step 1, but now with certain cycles imposed based on the step 1 features that we saw in the plots. And I'm going to show how to plot these estimated curves using the loop plot features of Mplus plotting. Step 2 can also be done for bivariate 2-level RDSEM, which I'm not going to talk about right away, but towards the end in the epilogue when we come back to the relationship between PA and tiredness. So we get that bivariate model once again that we looked at on slide 5. In step 3, we have an interesting step where you try to find deviations from cycles. We'll never find a model that fits perfectly, and we want to be able to capture deviations, and the deviations themselves can be of substantive interest. Now, cross-classified DSEM is again very useful for testing which deviations are significant in a very simple fashion. I'm going to show you how to do that. And then you can add those add model components that capture those deviations, that account for them, and you plot that together with also time-specific dummy variables that can be added. In step 4, only in step 4 do we go to random cycles coefficients. And I can do that both in 2-level and cross-classified RDSEM in Mplus. And once you have random cycles coefficients, that is cycles coefficients that vary across individuals, so different individuals have different cycles, then you can take step 5 and try to explain that variation across individuals by individual specific covariates, time invariant covariates, background characteristics of the individuals that can explain why certain individuals have, say, higher amplitude in their cycles. And in that connection, we're going to talk about the Mplus features of multiple imputation and translating to what I just mentioned, amplitude and phase of the cycles. On slide 7, I will show the modeling in terms of a figure, and throughout this talk I'm going to talk modeling in terms of figures and not formulas. For those of you who want the formulas, you have them in the paper. Now we're going to focus on the bottom part of the picture, ignoring this top part here. And you have one variable here, y, and if you go back to slide 5, you see then that corresponds to the top part of the picture, one outcome, and with a within part and a between part, not all of this other complexity. And that's how I want to start. I want to start univariate with a univariate model. And this part down here is what I call a DSEM model, Whereas when you add this top part here, it becomes cross-classified DSEM. So the DSEM part is what I discussed in Webtalk 6. So what you have here, you have two time points, t and t minus 1, and you decompose the observed variable into a between part, variation across individuals, between ID, and within individuals, that is, across time. And you see that these arrows go to the y box without any residuals. The residual is 0. That is, we just write y as yb plus yw. Simple algebraic relationship. Just decompose it. So then we can talk about within individual variation, where this within variable is regressed on itself at the previous time point. This is a lag 1 model. We could have a lag 2 model if we want to, with an auto-regressive coefficient rho here, and a residual in that relationship. In addition to that, y is influenced by this between level variation, which we call a random intercept. So this is the random intercept description of DSEM. And again, this is covered in Webtalk 6. And the interesting thing then is that when you write it this way, you have a direct translation to Mplus input, where the Mplus input, the model statement, the model command, has a within part and a between part. So in the within part, you have this regression that you specify, and the between part, in this case, just has a mean and variance here. But it could have a quite complex model here as well on the between. Now we're focusing in this web talk a lot on cross-classified DSEM. So it's a cross-classified model, and that is an expansion of regular DSEM to add this part, where for each time point we add a latent variable, a further decomposition, a time-specific component, capturing time-specific variation. So you have y for the between time component. The cap t stands for between time, and this is time point t. So this is like a factor, or latent variable, continuous latent variable at each time point. And these can be estimated, and these can be plotted. So this can capture, in an exploratory fashion, can capture cycles variation across time. And that's the nice feature of cross-classified DSEM. So on slide 8, we show the results of the analysis in terms of a plot. I'll show you exactly how the analysis is set up later on. But here is the result of it. We get a time series plot for these between time estimates that we achieve by doing cross-classified modeling. They are in blue, and we see them for the 7 weekdays here. So we see the cyclic behavior of the blue curve. No cycles function imposed, but we certainly see this feature of going up and then going down. So these are called, these blue values are called B2A in Mplus internal notation, between level 2A. Cross-classified has two between levels, between ID and between time. Between time is 2A. Minor detail. In any case, you see the red curve then, which is the means over subjects, follow this blue curve, or rather the blue curve follows the red, since the red is the data. But you have more fluctuation in the red curve, like here for instance. But we should remember then, as the paper points out, that many of these points are based on very few observations, very few people, and may only be due to one person, for instance. So we reduce the variation in the data by modeling it by the cross-classified model, but without imposing a specific cycles function. So no cycles function is imposed here. It's totally exploratory. We just have a multi-level model which stabilizes the graph, and it's an easier way to look at the data. It's a more succinct way to understand what the data is like. Now we already see some deviations here. Friday and Saturday, it seems like the observed means are a little higher than what's predicted by the cross-classified model. And those are the kinds of deviations that we're going to focus on as we go forward. On slide number 9, we see the step 1A input for cross-classified DSEM. We see the 3 parts: between person, between ID variation, within person variation, and a between time variation. So let's see how that plays out in terms of input specification. Use variable list is equal to PA. So PA is what Y represents here in the general notation. It's a univariate analysis, single variable across time. And now we have a cluster variable setting with 2 variables on the right-hand side: ID, that is person, and time. Then we turn to the t-interval specification. It uses a variable called hours, which is an original variable in the data set that is on the names equal list. And we're going to handle it in terms of 3-hour bins, 3-hour intervals, so that the 24 hours of the day is represented by 8 time points. The time variable that is such created is called time, and it ranges, it's an integer variable that goes from 1, 2, and up. And that's the variable then that you can name yourself, and it should be the same as the second cluster variable on the cluster option. And we work with the lag model, lag1 model, and that represents then what we have here, a lag1 YW on YW t minus 1. We could have lag2, lag3 models as well, but we have a simple case here. The analysis then is type equals cross-classified, and the estimator is a base. We can only do this using base estimation. B iteration stands for Bayesian iterations, and the value in parentheses says that we should do at least 2,000 iterations to make sure that we have a dependable solution. Number of processors is 2. Even if you specify, say, 8, you will only use 2 here in the computations. The model then corresponds to the 3 parts here, the different colors: the within, between ID, and between time. And ID is then the variable that you have here in the cluster option, and between time, that time variable is the same as this. So time should be the same in between these 2 and also over here. So on the within level then, we regress PA onto itself at the previous time point. This means that &1 means lag 1. So that corresponds to the specification over here. So that's that linear regression with a autoregressive coefficient that I call rho here. On the between ID level, we estimate the variance for this YB variable, and we also actually estimate its mean by default. On the between time level, we also estimate that variance. That's the variance of this variable up here. And that variance is then called PA, and on that level, the mean of that is 0. So mean of these are always 0. And note also that one cannot have relationships between the Y circles up here in the between time box part of the model. Now, what we're going to focus on is plots here to learn about what the potential cycles may look like their duration and shape. So we asked for factors, all factors, and 200 draws. So just a note here that by factors we really refer to any latent variable, not only a factor analysis factor like obtained by f by something, but also a latent variable like the yb here or the yt here. And if we wanted to have a random autoregressive coefficient here, then that random coefficient, that is a coefficient that varies across individuals, would be yet another latent variable or yet another factor. So if you focus on this variable here, the between time variable, which we want to estimate the values of and plot, what we do in the Bayesian analysis is, after the analysis has converged, this statement here asks the program to make 200 imputations. That is, you re-estimate the estimates and this value 200 times. So this value, this latent variable, gets 200 values. And then we take a look at the mean of that distribution of 200 values, or the median if we want to. So that's the posterior distribution. So just as a Bayesian aside, a latent variable like this is just like any unknown quantity in the model. That is, like any parameter. So it gets estimated, and we have a posterior distribution for it, just like we have a posterior distribution for a parameter. And we then choose a point in that posterior distribution. So these 200 draws then captures the uncertainty in that estimate. We're used to factor scores where we have only one value for a person, but you can also have several values, so you take into account the uncertainty, not only the standard error, but the whole distribution. Now, often it is sufficient to have maybe only 50 draws here. And actually, we have a paper on imputations that discuss how many draws you may need for different situations. So this is the setting. This is the input for the first step of analysis. So now I turn to demonstrating how we do the step 1A analysis. We're going to take a look at the output very briefly. Much of it is covered in Webtalk 6. We're going to focus on the plotting. And again, the analysis step numbers refer to table 1 in the paper, with the inputs given in supplementary material. And actually, that material shows more inputs than we discuss here in Webtalk 7. So let's take a look at the Mplus output for this run. So we have cross-classified analysis. So we have two cluster variables, ID and time, and we specify type equals cross-classified. And we have a within part of the model, a between ID part of the model, and a between time part of the model. And the first thing you want to look at is to see if Mplus has given you any warnings that you want to pay attention to. Here is about the data set containing missing on all variables. So you want to go back into your data to understand why that is happening. And then you take a look at the summary of analysis to see that the total number of observations is right, the number of dependent variables, independent variables is right, and also looking at the summary of data here. 219 clusters, meaning 219 individuals. And then we have clusters with different sizes, 6 meaning that this person, 238, was observed at 6 different time points. And we see here then that the total number of time points observed for anyone is 56. And most people, the typical value is a low 50 number of time points observed. But one thing I would want to look at pretty much right away is what's at the bottom here. namely the technical 8 output. Because if that's not alright, the results may be meaningless. So you want to look at the potential scale reduction factor here, PSR, and you want it to go down towards 1 and you want it to stay close to 1 for a long sequence of iterations. Quite often it happens that the PSR value goes down towards 1 for several iterations, but then bounces up again, and you may prematurely stop after too few iterations. So you want to keep going so you have a long sequence of PSR values close to 1. So let's take a look at the output here. You have 5 parameters, and the model results are given here for the within level and the between levels. So within level we have an auto regression between PA and PA at the previous time point. It's an autocorrelation, same as the regression or correlation coefficient, and you have a residual variance. So that's a moderate autocorrelation. Between time level variance here, 0.01, and then between ID, where you have the variance and also the mean, 5.687, which we'll keep an eye on as we go forward. And I also look at standardized model results, STD-YX standardization. There's not much to look at in this case because we don't have any covariates. But at least you see then you get an R² here at the end for the within level where you regress PA onto itself. So the R² is 0.138. Now let's take a look at plots. So we go to view plots and we select a plot to view here. We're going to focus on time series plots. And here you see the variables that come up, PA and B2A PA. B2A PA being the between time component of the model, the time specific factor values. So you have then a choice between the mean and the median in the posterior distribution for those factor values. And I'm going to choose the mean here most often. But let's take a look at the PA first. You see that you can show them for each subject, but also means over subjects like this. Okay. And you know then that we can add a timeline to mark the different days of the week, 8 hours per day, and we get this plot. Let's take a look at another plot in the time series category. Let's take a look at B2A, where it looks like this, and you have a mean line added here. That's while using this option, you get that mean line. So you have values below and above the 0 value for the between time component, that latent variable. Now you may want to add a variable. Let's say that we want to add in the sample values of PA to show in the same plot. And you get this message, which shows that you're mixing level 1 and level 2 variables. B2A is a level 2 variable only, whereas PA is on both levels, and we're choosing the average here. And you see then that you have a plot where you have the two outcomes on two different scales here. So what you want to do instead is to go back and take a look at the B2A with an offset value, And there comes the value that we looked at before, 5.687. And we put that in, and in that picture we can add the variable of PA. And here we go. There we have it, so that we can see how close they are over the different days. And if you've noticed, in this plot here, we have the colors reversed relative to the graph on slide 8. On slide 8 we had the B2A in blue, whereas here it is in the red curves. So let me take that as a motivation for showing some editing features. So we go down, right click and go to the edit plot, and we see then colors here, and for B2A we have red, and we wanted to change it to blue. And at the same time, let's also make the width of these lines a little bit thicker, and have 3 here, and do this similar thing for PA, which is blue, but we want it to be red, in line with the graph on slide 8. And then again, let's make it a little thicker, and let's say OK to that. And you see the thickness is better, and may show up better if you put it into a paper, for instance. Now up here in the legend, you see that the lines have also gotten thicker, and you can actually edit this legend as well. You can double click on this and you get a menu showing up, where you have many different options, but we're going to focus on the font. And you see then that we have size 12. How about if we try size 16 instead? And you see that the legend box is bigger. You can also click on the legend box and you see these broken lines and the little black squares here, where you can actually pull and extend the legend box. Same thing for this one in the middle here. Extend it like that, and then click to get it to be cleaned up. So those are some of the editing features you can use. Now we turn to step 2 of the 5-step analysis. So we're going to do cross-classified DSEM with cycles. And if we remind ourselves about the analysis steps on slide 6, we are now at step 2 here. So we did step 1, finding the cycles by an exploratory analysis, where the cross-classified DSEM used between time estimates for an unrestricted analysis of the cycles, just trying to find out what it looks like, what their duration is. And we also showed how to plot the observed means and the time-specific estimates. In step 2 then, we take a more confirmatory approach. We're deciding on a specific model, and we're going to talk about the so-called Cosinor model. We're still in the fixed cycles coefficients setting. That is, we don't allow the cycles coefficients to vary across individuals. Now we're going to take a look at the cross-classified DSEM with cycles and show how to plot the estimated cycles curves using loop plot. So on slide 11, we're focusing then on the cross-classified DSEM with its between time part, and we see that we have these latent variables y on the between time level, which now are predicted by observed variables which are on the between time level. So there are observed variables x1 and x2, which are 2 predictors of this latent variable. And that regression then has coefficients beta 1 and beta 2, and the residual as well. Now these 2 predictors are what we need to capture the cycles. they're not just any predictors. They're very specific predictors that enable a sine-cosine shape for the analysis. And our aim is to estimate these coefficients, which later on we're going to allow to vary across individuals. On slide 12 then, we take a look at the basic Cosinor model. The simplest Cosinor model, we're going to take a look at several different versions that are possible in the Mplus program. So the aim is to fit the cycles by regressing y at time point t on two covariates, x1 and x2. And those covariates have known values that are formed by taking the sine of 2 times pi, pi being the usual 3.14, and with a frequency index called omega and the time value t. And I'm going to talk about the frequency index in a second. X2 then uses the cosine function, and you have 2 times pi omega t there as well as the argument. So here you get a chance to practice your trigonometry knowledge, although you don't need to know very much at all. The omega component here is a frequency index, as I said, and in this case it's simply 1 divided by 8, where 8 is the duration of the cycle, and since we have 3-hour bins, 3 times 8 is 24, so the 24-hour cycle is represented by these 8 time points. So again, omega is 1 divided by 8. So we have a simple linear regression here with intercept and slopes beta 1, beta 2, and a residual. But what's interesting about these cycles coefficients, beta 1 and beta 2, is that they carry information about features of the cycles that have more of a substantive interpretation. So beta 1 is amplitude times this sinus component, which then includes a phi coefficient. So that is the phase coefficient. I'm going to say more about that in a second. And beta 2 is a times cosine, the same thing. So we estimate two coefficients, beta 1 and beta 2, but they correspond to two other coefficients, amplitude and phase, which have more of a substantive interpretation. Amplitude is defined as half the difference between the highest and lowest y values. So that's a shift in a vertical direction. Phi is a phase shift. So that's a shift in a horizontal direction. And omega is the frequency index I mentioned. And we have these relationships. Amplitude is the square root of the sum of the squared beta coefficients. So when the beta coefficients are high, amplitude is high. Now the phase shift is a little bit more tricky. It's tan inverted of the ratio, which is harder to see through directly, but we're going to talk about it in a more tangible, down-to-earth way on the next slide. And actually, this equation 5 isn't as simple as it's depicted here, and it's often depicted in writing. Section 2 of the supplemental material discusses the details of that phi definition. So on slide 13, we are looking at examples of Cosinor curves, 4 of them, and for the case of omega 1 divided by 8. So we have 8 time points here in day 1, 8 time points in day 2, 8 time points in day 3. So you can think of it as 3 different days. So you look at it in a very broad fashion then. At the top, you can consider this to be a curve for tiredness. You know, tiredness is low in the middle of the day, higher in the morning, higher in the evening, whereas at the bottom those curves may represent positive affect, but the positive affect is high in the middle of the day, lower in the morning, and lower in the evening. Now, if you look at the top curves, then you have B1 and B2 correspond to beta 1 and beta 2. So here the sine and cosine components have the same weights, same coefficients. So that's the red curve here. And you see then that the red curve has a higher amplitude from low to high. It's higher than for blue. So higher amplitude for red, and that's because the sum of the square root of the sum of the squares of these is higher than for the blue curve, where beta 1 is only half as much as in beta 2. So depending on the weights of the square roots of them, sum of the square root of the sum of the squares, rather, hard to say, you get different amplitude. But you also see that the curves are shifted sideways by emphasizing sine or cosine more. So for instance, the red curve peaks later at night. These are people who are tired after midnight, have their tiredness peak there, whereas the blue curve, they get tired, they have their peak a little bit earlier. So that's the shift in phase sideways that we just illustrated. Now, the difference between the top and the bottom is simply a change of sign. So that simple sign change captures the difference between tiredness and positive affect. On slide 14, I point out that there are different kinds of Cosinor model versions that you can do in Mplus. Different levels of generality. So I've listed here the models and how many parameters each model has in the standard univariate case, single outcome, and in parentheses the run numbers referring to the analysis steps of table 1 of the paper. So the three main categories are two-level RDSEM, cross-classified DSEM, and cross-classified RDSEM. So let's talk them through. The two-level RDSEM can be considered the standard Cosinor model used in the literature. It's been used both in medicine and in psychometrics in many different applications. So you have the cycles modeling on the within person level. And we have two versions of each of these three main categories: the fixed cycles coefficient and the random. For two-level RDSEM, the fixed cycles coefficient case correspond to that slide 12 that we just looked at. Slide 12 here, this model, where this residual has an autoregressive feature added to it. So this model has 6 parameters. I call it run 2C. Now the random cycles version of that, in that case, has 11 parameters, 5 more parameters coming from the variances of the two random coefficients, 1, 2, and the covariance between them, and their covariance with the random intercept, so 2 more, 5 parameters more, adding to 11. Now, I will focus in my demonstration here on cross-classified analysis of cycles, because step 1, after all, was a cross-classified analysis, and we can stay in that framework a little bit longer. So we're going to look at 2 cases: cross-classified DSEM, where the cycles are on the between time level, and cross-classified RDSEM, where the cycles are on within, just like for 2-level. So the cross-classified RDSEM, cycles on the between time level, in the fixed cycles coefficient case, that is exactly the slide 11 model that we looked at earlier. This model, fixed coefficients, and the cycles modeling takes place on the between time level. So that's there. And that model has 7 parameters, and it's run 2A. So here we see already that this model, fixed cycles coefficients for cross-classified DSEM, has one more parameter than the two-level RDSEM, so slightly more general due to the addition of a variance component for the between time level. Now the drawback of this is that we cannot work with random cycles coefficients. This model is not available because the cycles are on one of the two higher levels, and therefore you cannot make them random. Instead, we go to the cross-classified RDSEM with cycles on within. So whenever the cycles are on within, it becomes a residual DSEM model, just like it is for two-level. And in this case, we can work with fixed cycles coefficients. It's a 7-parameter run, and we can work with random cycles coefficients, 12-parameter run, adding the 5 parameters like we discussed. So this is a model that we're going to turn to towards the end of the talk. But right now we're going to focus on the cross-classified DSEM, particularly the fixed cycles coefficient case. Note also that the models used in the cross-classified fixed coefficient runs 2A, this one up here, and 3B. They both have 7 parameters. They're actually equivalent, those two models. The benefits of the 3B approach, we're going to talk about that when we look for significant deviations from the cycles. So although this is a little bit more of a time-consuming run than this one, it has some benefits in terms of easily finding significant deviations from the cycles. Now on slide 15, we turn to looking at the results of the step 2A analysis, where we have a cross-classified DSEM Cosinor analysis, the fixed case, where we have the plots of cycles in red and between time estimates in blue. So again, the blue are the between time estimates and the red are the cycles curves. You see the cycles, the red curve here, going up and down in a very regular fashion. And they're trying to fit to the blue curves, the between time estimates. And they do a reasonably good job. We have a fairly high R-square value, 0.41. Now, how did we do that? You have the input here on slide 16. So we have 3 use variables, PA and X1 and X2. We have cross-classified, so we have 2 cluster variables, ID and time. And the t-interval statement is again the same as before, hours coming from the names list, and 3 hour bins, 3 times 8 being 24, and time is our new time variable. And that is supposed to be the same as the cluster variable that you have there, same name. Now on the between time level that we designate like this, we vary X1 and X2. We let them be between time variables only. They only vary on the between time level. And we have a lag1 model for positive affect. And then in the define command, we create these X variables. So sine and cosine, where 6.28, etc. is 2 times pi. And then 1 divided by 8 is the W, and time is the T that we had in the formulas earlier. Same thing then for cosine. I've used a lot of decimals here to get good precision. And then we do a cross-classified analysis using the base estimator. And you may want to use thinning 10 here to not record as many, skipping every 10th, and maybe also getting more reliable standard errors because you have less autocorrelation in the draws, in the iterations. Slide 17, the model continues. The model refers to the within part, the between ID part, and the between time part. So now on within we still have this auto regression of lag 1. Between ID we'll let PA vary, and we're going to use the intercept, or the mean rather, of PA in a formula later on, so we give a label P0 for it. And then we have the between time part of the model where PA is regressed on X1 and X2. So that refers to this slide here. PA regressed on X1 and X2. We have these coefficients beta 1 and beta 2. And we give those coefficients the names of parameter 1, parameter 2, so that's beta 1 and beta 2. And then we add a model constraint section to do a loop plot. We have a loop of time going from 1 through 56. That is all 7 days. 7 times 8 is 56 with step 0.1. And we plot PA cycles and also what I call factor score cycles. So that's the between time specific estimates that we call B2A at one point. So the PA cycles is the mean plus P1 times the first X, which is this, X1 here, and P2 times the second X, which is the cosine part here. And the FS cycles is the same, but you don't add the P0, so you have that on a different scale, so to say. And you have the usual output standardized Tech 1, Tech 4, Tech 8. And you want to plot this, and you want to have a good amount of factor draws, 200 in this case, to get good estimates. So here is a demonstration of the plotting for the analysis 2A. First I'll talk about how you insert a loop plot in the time series plot. That is how we get the graph on slide 15. And then in that context I will also talk about saving plot data, which is useful for plotting curves from different analyses outside of Mplus. And just going through that briefly here, in the plot data in the 2A model, column 1 gives x-axis values for the 8 time points per day. So the column 1 values range from 1 to 56 for the 7 days. Column 2 gives the corresponding estimated B2A value, so 56 values. Column 3 then gives x-axis values for a loop plot which uses a certain chosen step. I've used 0.1 here to get a smooth curve. So there will be more x-axis values in column 3 than there are in column 1. Column 4 then gives the cycles values in the loop plot, and they therefore repeat. After 8 days after 8 time points you start over with the same value at time point 9, 17, etc. So we have 4 columns in the 2A setting. In the 1A setting you only have 2 columns. The x-axis values for each time point and the B2A values. You don't have any loop plot there because you don't have any cycles function in post. So turning now to the actual plotting of the cycles functions using the loop plot, let's go to the Mplus output and look at the time series plots again. And we're going to focus on B2A, and we'll look at the mean of it in the posterior distribution. And we're going to add an offset here to get it on the scale of PA as before. So here we have it. And now we can add the timelines again. To keep track of the days. Now we right click and look for Insert Loop Plot. And we put B2A on the scale of the PA variable. So what we want to compare it to is the PA cycles version, which has that extra intercept in it, according to the model constraint. So we add that, and lo and behold, here come the cycles. So we see that the, if you get rid of that for a second, we see the Tuesday, Wednesday, Thursday, Friday, Saturday. We see a deviation on Saturday where the cycles tend to underestimate the time-specific estimates from the model. But overall, it seems to follow the development quite well. There will be deviations, but it follows it quite well, I think. And this is the same as slide 15. Now, if you want to save data from this, and I'll show you a reason for it shortly, why you would want to do that, you would save the plot data, and you would give a file name down here and just save it. And the file that gets saved has the column structure that I just discussed on slide 18. Let's for a moment turn back to slide 15 and the step 2a analysis, where we impose a certain cycles function. That is, we do a Cosinor analysis. What we showed here on slide 15 are the cycles in red and the between time estimates in blue. They look like they're fairly close to each other. We have this R² value of 0.41, which isn't too bad. But there's something that's not quite right. And that's the fact that the estimated between time values, the blue ones, are estimated from the model where we impose the cycles function. So they are artificially close to the cycles because of this. What we really would want to do is to compare the cycles, the fitted curves, to between time estimates that are not obtained from the model with the cycles imposed. So that would be the same as looking at the model of slide 8 in the step 1a run. Those are the unrestricted between time estimates, not guided by any specific cycles function. They would be more neutral, so to speak, more closely related to the data, and therefore give a more correct assessment of the fit. The step 1a curve, the blue curve of slide 8, we call those estimates unrestricted between time estimates, not restricted by any particular cycles function. So I just want to repeat that and point out, because we have the option of presenting a more fair assessment of fit. And that's what we show on slide 19. Here we have a Cosinor model, but it's obtained from 2 runs. The cycles are the curves that we looked at before. Now, however, these red cycles are the same, but now they're paired up with the slide 8 between time estimates, the so-called unrestricted estimates, in blue. So now you see a slightly different blue curve than what we had before on slide 15. But I would argue that the discrepancies are occurring in the same spots. For instance, for Thursday here, and for Saturday. It's Thursday overestimation, Saturday underestimation. If you compare that to slide 15, going back to that, you have the same phenomenon. Overestimating Thursday, underestimating on Saturday. So the picture that we have here on slide 15 is not too misleading, but I just wanted to show you that you can actually produce the curves that give a more fair assessment. But it would have to be from two different runs, as I point out here on slide 19. And that's why I wanted to show you on slide 18 how you do the saving of the plot data to produce the values. So you save the plot data from the two different plots, and then outside of Mplus you can therefore create a plot like on slide 19. On slide 20 I turned to step 3, namely finding deviations from the cycles. And the paper discusses 3 different alternatives that we're going to use 2 of. One is to add simply a dummy variable for certain days, or actually for certain time points, which is what we're going to do. And then you just check for significance of the effect. So that's step 3a, the step 3a run, where I use the loop plot to show the effect of that dummy variable. Second is a DSEM approach, Bayesian structural equation modeling with small variance priors. That one is discussed in the paper, but we will not talk about it here. And the third one I find very useful, and that is to use cross-classified RDSEM, residual DSEM, to find significant deviations from the cycles. And that's the step 3b run that I'm going to show you, and where you can save data that gives you information on which deviations are significant. So how is this done? Let's take a look at the step 3a run first. And on slide 21 you have the input. So the use variable list is expanded to having not only the two sine-cosine covariates, but also a Saturday dummy variable that we're creating here later on in define. And since it's cross-classified DSEM, we have 2 cluster variables, ID and time. T interval stays the same as before, and as before we put on the between level the x variables, the sine-cosine variables, and the Saturday dummy variable. So we put it on the between time level by putting time in parentheses here beforehand. I mean, it could also be between ID, so we have to make sure we're pointing in the right direction. Still a lag1 model, still x1 and x2 created this way, but now we add this specification that creates a dummy variable Saturday 1 or 0. So if you just think about it for a second, the study starts on a Tuesday, so Saturday is day 5. So before Saturday we then have 4 days with 8 time points, so 32 time points, and the end of Saturday is then 5 times 8, 40 time points. So Saturday ranges between time point 33 and time point 40. Here I actually cut off the first time point and the last time point of Saturday. Saturday again lasting from 33 to 40, but I'm saying greater than 33 and less than 40 because I didn't want to cover the whole day. I got a higher R-square for the Saturday edition if I limited myself to interior points, so to speak. Type equals cross-classified, base, B iterations, everything's the same. And the only thing that's different then is that on the between time level, we have now added a Saturday predictor, PA on Saturday, that we give the label P3. On slide 22 then you have the loop plot, where the only new feature here is the Saturday designation of the Saturday effect. There the label P3 comes back in, and it says that we should add that in the interval of time points 34 and 39, including 34 and 39. So once again, cutting off the first time point 33 and cutting out the last time point 40 from the full Saturday range. And you can, if you have, say, a Sunday effect, you can just add that P4 times the Sunday time points that are relevant. So then you have a PA total, which is the PA cycles that we had before, plus Saturday. And if you don't want it on the PA scale, but on the B2A scale, on the factor score scale, you take the F cycles without the P0, adding Saturday. So let's take a look at Mplus output to see how that shows up. Let's look at the plot when we add this Saturday dummy variable. Let's work with the observed PA variable averaged over subjects, and we'll add timelines for clarity. So we have Tuesday, Wednesday, Thursday, Friday, Saturday. And what we do now is, as before, we insert a loop plot. And let's pick the PA cycles. And that's the part without the dummy variable. And we see then that on Saturday, the cycles underestimate the average positive affect development. And that then says that these adolescents are more excited on Saturdays than predicted by the cycle's behavior. You have other deviations too, but let's focus on Saturday. And we're going to take a look at these points, time point 34 to time point 39. Now, if we change the loop plot a little bit, we can look at the total, PA total, which adds the Saturday dummy, and it looks like this. So now you have this increase up here, better matching the higher excitement on Saturday for these adolescents. On slide 23, I turn to the third alternative of the step 3 finding of significant deviations from the cycles. And we're going to use cross-classified RDSEM, residual DSEM. The point here is that the cycles are estimated on the within level instead of the between time level. Before we had the two cycles variables x1 and x2 up here, now we have them down here in the within part of the model. That's also where a two-level analysis puts them. Now, the advantage here then is that deviations from the cycles can be captured on the between time level, because we have these time-specific latent variables on the between time level. So let's look at how this is done. And let's take a look at the step 3b, I call it, that run. The input is like this. You have the same setup as in 3a to a large extent. The only thing that, or one of the important things that changes, is that the within specification is used for x1 and x2. So the sine cosine covariates are on the within level instead of the between time level. And therefore you have the x1 and x2 on the within level here, whereas the between time level has only this PA component, which will show you deviations from the cycles. Now on slide 25 then, you have the same setup as before. And we are not adding any dummy variable here for Saturday. Same setup as before earlier on in 2a. But what's new here is this. We save data here. We save factor scores, 200 of them, with thinning of 10, that is we skip every 10, and we save that in a file factor score cycles deviations.data. So we're going to take a look at that in the Mplus output and talk about how that creates a way to test for significant deviations based on the between time specific values. In the save data command of the 3b run, we saved a file fs cycles deviations.dat, and at the end of the output you see the order and the format of the variables, the different columns of the data set saved, with a PA variable, the Cosinor variables x1, x2, the original hours variable, and the new time variable. And what's highlighted here then is the B2A for PA. It's mean. You can also use the median. And then we also have the standard deviation down here. And what you can do then is to take this file into another software like Excel and calculate the ratio of the mean divided by the standard deviation to get an approximately normal z-score variable. So you can check if that ratio exceeds 1.96 in absolute value, and you see at which time point or which time points that happens. So that is a way to use 3B analysis to find significant deviations from the cycles. To summarize the step 3b run, let's go back to slide 23 and once again take a look at the model. So it is a cross-classified DSEM model where the cycles variables are on the within level. So that's the reason why it's called DSEM instead of DSEM. That is, the dynamic relationship is not between the YW variables, but between their residuals once we have taken out the effect of the cycles. So it is a cross-classified DSEM with cycles estimated on the within level instead of the between level. Now, to remind you further then where we are in the big context, if you look at slide 14, we talked about the different Cosinor model versions in Mplus, and what we just did was a cross-classified DSEM cycles on within fixed cycles coefficients. So the 7-parameter run here, run 3b, which is equivalent to the cross-classified DSEM fixed cycles coefficient run 2a here in terms of model fit and parameter estimates, but it affords 3b affords the advantage of looking at significant deviations. But they're the same model, and you also notice that this cross-classified DSEM with fixed cycles coefficients has 7 parameters. That is, it's a little bit more general than the fixed cycles coefficient run within the 2-level DSEM, which has only 6 parameters. And the difference is that between time component that gets added with cross-classified. Sometimes you don't need that, and 2-level DSEM is just fine. Now we're turning to step 4, fitting cycles using random cycles coefficients. That is, coefficients that vary across the individuals. So that's the Cosinor model with random beta 1 and beta 2. And just to remind you where we are in the big picture, let's go back to slide 6. And we are now in step 4 down here. We've gone through finding the cycles, fitting the cycles, finding deviations from the cycles, and now we're to fitting cycles with random cycles coefficients, and the ending step is explaining those random cycles. So back to slide 26. We are focusing on two kinds of models here. We know that we have many Cosinor model versions. We have both two-level RDSEM and cross-classified RDSEM and DSEM, and within each we have fixed and random coefficient versions. Now we're focusing on the random cycles coefficient versions. So two-level RDSEM, coefficient variation on the between level. Of course, the Cosinor covariates are on the within level, and that's what gives rise to the residual DSEM notation. Now, this two-level analysis is suitable if you have a small residual variance on the between time level from the derived from the step 2a analysis. And that may be a reasonable approximation in this case. However, there is also the cross-classified RDSEM, which we took a look at in the 3b run, where we used a model with cycles on the within level, and which would then allow coefficients variation on the between ID level, just like on the between level in two-level RDSEM. But it's much more time-consuming than two-level analysis. So we're going to focus on the two-level RDSEM, but it is possible in principle to do this step 4 using cross-classified RDSEM as well. On slide 27 then, I point out that what we want to do when we have established random cycles coefficients is to try to explain that variation across individuals by covariates, background characteristics for the individuals, time invariant covariates. And that interpretation of the cycles is much more clearly done by translating the beta coefficients to amplitude and phase. It's true that beta 1 and beta 2 effects can be understood in terms of emphasizing the sine or the cosine coefficient and its impact on the cycles. We saw that in an early plot, but it gets cumbersome to work in that metric. It's better to focus on the amplitude and phase, the vertical variation and the horizontal variation. And that can be done very efficiently in a two-step analysis. In step 5a, the first step, we do a two-level RDSEM with between-level covariates, where we do multiple imputation at the end of the run for the random beta cycles coefficients using a save data command. We're going to take a look at that. For example, as it says here, you can ask for 200 plausible values. That's the 200 value that we've seen before. 200 draws from the posterior distribution of the two beta coefficients for each person. So therefore, there are 200 data sets, and each of the data sets has n rows, the number of rows that you have in the original data set, or at least in the data set that is analyzed by t-interval. And the columns are the two random coefficients and the between level covariates. That is the between level components of the model. Step 5b then is a single level analysis using type equals imputation. That's the analysis type, and actually it's the data type, and translation in the define command of the beta coefficient into amplitude and phase. So for instance, we see the amplitude for individual I is that formula we saw earlier, square root of the sum of the squares of the beta coefficients. And once we've translated them into define, we can then regress the amplitude and the phase on the covariates, the between level covariates, in a single level analysis. Doesn't even need Bayes. On slide 28, I talk about step 5 in terms of cycles for factors behind the PA items. So we're going to do step 5A and 5B for factors. And what do I mean by that? Well, we have 6 PA items: relaxed, satisfied, confident, happy, energetic, and excited. And what we've done so far is to use a PA variable that is a sum of those 6 items, 7 category items. But a multi-level factor analysis, a 2-level factor analysis, actually show that there are 2 factors. And they can be characterized this way. You have, for the first factor, you have strong loadings for the relaxed, satisfied, and confident items. And for the second factor, you have high loadings for being happy, energetic, and excited, with a cross-loading for the happy items loading on both factors. And that corresponds to how the researchers here of this study characterize the items. They characterize these first 3 items as low arousal items and the last 3 as high arousal items. So there's a little bit of a misclassification with respect to happy. It loads on both factors. But you have a clear separation between the factors. This is on the person level, variation across people, and this is on the within level. You have the same structure, just a little bit lower loadings. And the 2 solutions also differ in terms of the factor correlation. Factor correlation for between person factor analysis is 0.83, and for within it's 0.65. And you see a similar situation in two-level factor analysis in general, where between level factors are more highly correlated than within level factors. So the modeling that we're going to do is looking at cycles for these factors, and we're looking at them for the within level factors, the less highly correlated factors. That's where the cycles are going to be specified, not for the between level. Slide 29 shows the result of the factor analytic cycles modeling. So at the top we show the curves for the low arousal factor, and at the bottom the high arousal factor. So we have the same 7 weekdays, and what we're showing here is red being the cycles curves and the blue being the factor scores that we get at each time point. So these are factor scores that are estimated due to the by statements. So actually a factor measured by the PA items. So here we get those blue estimates, and again we see this deviation on a Saturday, perhaps on Sunday as well, where the cycles modeling underestimates the PA level, the low arousal PA level. We also notice that the low arousal factor variation is a little bit higher, has a higher amplitude than the high arousal factors. They're on the same y-axis scale. Now, the high arousal factors, they seem to follow the cycles. Cycles seem to follow the data, or the factor scores rather, quite well here, and you see that reflected in the R-square values being 0.48 for the low arousal factor and 0.59 for the high arousal factor. So we have a more pronounced cyclic behavior for the high arousal factor, and in the epilogue we're going to see a potential explanation of that phenomenon. Now, how is this done? How do we get here? Well, let's take a look at slide 30. which looks quite complex at first glance, but let's go through it slowly. So we're in the setting of two-leveled DSEM with random cycles coefficients and factors related to time invariant covariates. So now we're going to bring in the covariates, and we have then, if we focus on the upper right hand side here, we see the 6 PA items. They're observed variables, and they're measuring two factors, F1 and F2, low arousal and high arousal, and with PA4 being the happy item, which is influenced by both factors. And on that within level, we have the cycles covariates X1 and X2. They are within they're time varying covariates, we can call them, so within covariates. And they influence the two factors differently. So factor 1 is influenced by this arrow and that arrow, and factor 2 by this and that. And we see that all 4 arrows have filled dots on them, so they are random coefficients varying across individuals. And therefore, on the between level, those random coefficients become latent variables, open circles, which we want to relate to background variables. In this case, gender, STQ, a measure of childhood problems, age, and tiredness average across time. On top of that, we have between level variation in the items. For each item, we have a random effect, a random intercept, and it is then measuring the two factors on the between level, F1 and F2, the ones that had a higher correlation than the ones on the within. Note then a couple of details here. On the within level, we call it RDSEM because we are looking at the residual relationship between the factors. F1 has a residual relationship to F1 at the previous time point, same for F2. So there's no relationship between F1 for time point t and F1 for time point t minus 1, but it's for the residual. So it becomes a residualized relationship, so hence the R there. Second detail to notice is that this picture is simplified. We don't have the usual connection between the random intercepts, which is for each item, and the observed boxes here, the observed variables up here. That would just make the picture more messy. But it should be understood that these variables, these random intercept, influence the observed variables here. So we have the same latent variable decomposition going also in this picture. It should be understood that it's going on there. So here's how the input looks for step 5a, the picture that we just looked at. So the use variable list then has all of the 6 items, PA low arousal 1 through PA low arousal 3, PA high arousal 1 through 3. And then we have the time invariant covariate and the cycles variables. One cluster variable only because it's 2 level, and the cycles variables are on the within level as we mentioned. And the between statement then refers to the time invariant covariate. T interval does not change. And here we create an average of tiredness. That's a cluster mean, so we average across the time points and get a cluster mean variable. And we also designate girl as being the dummy variable of interest. X1 and X2 is the same. And then we center the covariates by grand mean centering to simplify the interpretation a tiny bit. Then we have 2-level random here. We have to add random because we're going to have random effects. Estimator base, and now we increase the B iterations to do at least 25,000 iterations because these factor models are more complex in terms of the analysis. Turning then to slide 32, we see the factor specification. So on the within level, we defined the factor for PA1, that is the low arousal factor, and for PA2, the high arousal factor. And we do that by freeing all of the loadings and then fixing the factor variances to 1, so setting the metric in the factor variance. And we have a lag1 model, so that's in parentheses &1, referring to the fact that we want to lag this variable, have it be regressed onto itself at an earlier time point, well, at least the residual of it. And if you want to have an equality, you put that in parentheses also. And we're not going to use that in this run. I used that in a cross-classified version. But that's where you would put it. Similarly here then for the high arousal factor, where I put an asterisk for the first one here. It comes in a separate order, so I can't use the list function. I put the most prominent item first as sort of the leading indicator of the factor, just to help with the estimation a little bit. But here comes then the factor regressions onto the cycles coefficients, cycles variables rather, x1 and x2, for the first factor and for the second factor, and we're making those random. So here are the S11 through S22 filled circles in the picture that we looked at. So we regress those factors onto the cycles coefficients, cycles variables rather, and then we take the residual of that as autoregression. So PA1 on that residual on PA1 residual at a time point earlier on. And same thing for PA2 on PA1. And we even have the crossed relationship. So PA1 can be regressed on PA2 and vice versa. So what I'm looking at are these relationships here, these over here, these residual relationships. Then on the between level, you have the between factor 1 and 2, and the same specifications as up here, and no equality across within between, because very often the between loadings are bigger. And I also fixed the variances to 1 here, and I let them be correlated. And I give that a label, which I'm going to discuss in a minute. And I do that because I want to have a way to stabilize the estimation, the algorithm, the Bayesian algorithm, because these are highly correlated factors, 0.83, and that creates a little bit of a difficulty for the estimation. In fact, you could just make this into one single factor. One factor for all 6 items if you wanted to. It wouldn't make much of a difference to the gist of the analysis. And then the key step here, we regress those factors and the random slopes within slopes onto these between level covariates. On slide 33, the input for the 5A run continues with a model prior statement. So that refers to the parameter labeled as C on the previous page. Down here, the factor correlation. We fixed the metric in the factor variance to 1, so that's a correlation. And because the factors are highly correlated, we want to help the algorithm, the iterations for finding the estimates, by imposing a mild prior here, an inverse Wishart distribution prior, 0.3. It implies, without going into details, it implies that the prior for this factor correlation is uniform in the range of -1 to +1. So in the range of a correlation. So that helps protecting us from iterations where the factor correlation goes beyond those bounds rather. For instance, going above +1. The rest of the input here concerns the save data statement, and that is a critical one here in step 5a, because we're going to do imputation at the end, as we discussed. This file name using the word imp with an asterisk implies that we're going to have a set of data sets, namely 200 data sets, as we mentioned. 200 data sets are going to be generated with between level components, including the random slopes for the factors on the cycles. Now the regression coefficients on between that you get from slide 32 here, note that they are in the metric of S11 to S22. That is, they are in the metric of the X1, X2 covariates. So they are the beta 1, beta 2 coefficients, random coefficients for each of the two factors. And we discussed the fact that the beta coefficients and their relationship to background covariates is hard to interpret, and that we instead want to make a transformation of those coefficients into amplitude and phase for each of the two factors. So as a first step towards that, we therefore do imputations of 200 data sets here on slide 33. And that's going to move us towards an analysis where amplitude and phase are instead regressed on those covariates. That is, getting to step 5b. So in step 5b, then we start with the data command, file equals fscov imp, and then we add list instead of the asterisk, and we do a type equals imputation analysis. So here we have then an analysis that's repeated for each of the 200 data sets that we created, that we imputed in step 1 and 5a. And the type imputation runs is done for each of the 200 data sets, and we take the average of the estimates and compute the standard errors in line with imputation formulas, as usual in imputation. Now the variable list here then is consisting of only between level variables, the covariates, and the between level factors, and the random coefficients, which also are on between. And we also get factor scores for each of the 6 factors. Now here then in define, we do the transformation from the S variables to amplitude for factor 1 and for factor 2. Down here is a complex statement that really only checks the signs of these random slopes. Here we have 6 cases of combinations of signs for the first factor, and then on the next slide we have it for the second factor. So the signs are positive, positive, negative, positive, etc. And that is described, these are the issues in computing phase. Phase for factor 1 on this slide and phase for factor 2 on the next slide. The intricacies of computing phase is discussed in the appendix in the paper and its supplement. and I'm not going to discuss that here, but it is a critical issue for, particularly for Bayesian analysis, to do it in this careful way, taking into account the signs of these random coefficients. But all in all, we're just computing phase for factor 1 and here for factor 2. Now on slide 35 then, we also have some novelties. We have FB iterations as the standard, so fixed number of Bayesian iterations set at 2000 for instance. And we want, that's why, because we want to use the same number of iterations applied to all of the 200 analyses. So that's just a convention we use. So the real issue here then is the model. And here we have then the between factors, the amplitudes for the two factors, the phases for the two factors, regressed on the time invariant covariates. So it's a simple regression model. We have 1, 2, 3, 4, 5, 6 dependent variable regressed on a bunch of covariates. Very simple model. So the analysis is single level, could be done by ML as well, but we do Bayes here. And then we just tack on a labeling of the coefficients. Here we look at the intercept in that regression, and here then it comes in handy that we did the grand mean centering of the covariates, so the intercepts are the same as the means. And then we can add a little model constraint feature to it, where we look at difference between the factors in amplitude, like we saw that the amplitude was lower for the high arousal factor. We can test if that difference is significant, and same thing for the horizontal shift, the sideways shift in the phase, to see if that's significant. Now some of the results then are as follows, and they're given in more detail in the paper. Turns out that both of the two between level factors are significantly influenced by SDQ, childhood problems, in a negative fashion. So with more childhood problems, you have lower between level factors for positive affect. And you also have a negative relationship from or to the average of the tiredness. That's not the main focus of the analysis. We are really more interested in how the amplitude and phase relate to the covariates. And we find then a difference between the first and the second factor. So for amplitude 1, that is significantly influenced by age in a negative fashion. So the older the kids are, and they vary I think in age between 12 and 16, the older they are, the lower the amplitude for the low arousal factor. But there's not a significant difference with respect to age for the high arousal factor, AMP2. So that's a substantive finding that substantive experts can ponder and interpret. Both amplitude 1 and 2 are also positively influenced, significantly so, by the average tiredness. Similarly, there's a difference between the factor in the phase influence. So phase 1 for the low arousal factor is significantly influenced by average tiredness, so that higher tiredness makes for a higher phase, so a later peaking within the day. For the phase 2, for the high arousal factor, there is no such or no significant influence from any of the covariates. On slide 36, I return to the topic introduced in the prologue, namely the relationship between positive affect and tiredness. We saw an inverse relationship between those two outcomes, tiredness in blue and positive affect in red. And we asked if tiredness follows cycles due to a circadian 24-hour rhythm, and we asked if such cycles also affect positive affect. And we've studied positive affect now, both in terms of the observed sum score and in terms of factors, and find that there are these cycles also for positive affect. And we're ultimately interested in then the relationship between tiredness and positive affect after accounting for the cycles. Is there something else in positive affect than just not being tired? As a first step in that then, let's take a look at an analysis using the 2A approach. Namely, modeling cycles and having fixed cycles coefficients. Now this is for tired only, so this is a univariate analysis, just like we started off with a univariate analysis for positive affect. And we do this in a cross-classified DSEM setting, just like we did before in step 2A. And what you're looking at here is a plot of the cycles in these consistent curves across time, and the between time estimates, which are sometimes a little higher, sometimes a little lower than the cycles themselves. So for instance, on Saturday here, it seems like these individuals are less tired, low value on tiredness, than predicted by the cycles. So they are perky adolescents midday on Saturday, much more so than the cycles curve predict. And we see then that we have a very tight relationship between the two curves, and it's reflected in a high R-square value of 0.73, whereas R-square for the positive affect was only 0.41. So focusing on the main topic then of the epilogue, we are going to use a two-level RDSEM based on the two factors that we have found and relate that to cycles and to tiredness. So it's a bivariate analysis of PA and tiredness, but building it on top of a two-factor factor analysis like before here for the 6 items and the 2 factors. So this is a two-level model, so we have within here, I don't show the between model. Here are the 2 factors, here is the tiredness within component, and here is the observed tiredness variable. So it's very much like slide 5, where we looked at this model for an observed PA variable, the sum of the items. But in this case, instead we have the 2 factors, and then we have the cycles variables x1 and x2, which influence tiredness and influences the factors as well. And we have, for simplicity, no random cycles coefficients here, no filled circles. And also, for simplicity, we are not going to involve any time invariant covariates like in the previous analysis in step 5. Although we could add them for the between level parts of the factors, so F1B, F2B, and tired B, that is the between part. But we haven't done so in this analysis. So you look at this picture then, you see then we have a residual coming into tiredness and the residual coming into F1 and to F2. And we're asking if what's left in tiredness after we've taken out the cycles influence, after we've counted for that, what's left? Does that influence the residual in the 2 factors after accounting for tiredness, for the cycles in those two factors. So it's a residual relationship that we're looking at here, going this way and going that way. A little intricate drawing here, but this is in line then with slide 5, except that we generalized it to a two-factor situation. Here's the input. The left-hand side looks the same pretty much as it looked for the two-factor analysis in run 5A. And we have the same number of B iteration, 25,000. I don't think it's quite needed here for two reasons. Because we're doing two-level RDSEM instead of cross-classified analysis. And also we're not having random cycles coefficients, but actually fixed cycles coefficients. So let's take a look at the details of the model here on the right. So you have the first factor, the low arousal factor for PA, measured by the low arousal items, and then the second factor, the high arousal factor, specified in the same way as before. So ampersand 1 being a sign that we can use lagged effects for these two factors. Further down here in the model, we set the metric in the factor variances, we regress the factors on the cycles variables, and we also regress tiredness on the cycles variables. So now what's bolded here then is what's of primary interest. We use the hat notation to regress the residuals of the two factors on the residual of tiredness. So the residual in the regression of the factors on the x1, x2, and the residual of tiredness regressed on x1, x2. Just in line with the model figure that I showed on the previous slide. So that's the key relationship that we're interested in. Is there any relationship there? Is there any significant influence of the tiredness variable taking out the cycles on the factors taking out the cycles? And then you have an auto-regression here, like before, for the factors and also for tiredness. On the between level then, we have two between level factors once again. And the question is once again whether that's really needed or if we should just have a single factor here. I'll speak to that in a second. And we regress those two factors on tiredness here, thinking that tiredness is a predictor, relevant predictor also on the between level. And here's where we could add time invariant covariates influencing both the factors and tiredness if we wanted to. So here then is what we found. Excerpts from the output in standardized form. So on the within level, here is the residual for the low arousal PA factor regressed on tiredness. Significant effect in the sense that the confidence or credibility interval does not include 0. It's negative. It's a small effect. Whereas if we look at the high arousal factor, we have quite a much larger effect. So that tiredness does have a significant and strong effect on the factors, or at least the factor of the high arousal kind, being excited and the like. So here we see a strong difference then between the factors. They're clearly, the fact that there are two factors is validated by this influence from tiredness, where tiredness has a very small effect on the low arousal, but a stronger effect on the high arousal factor. So yes, positive affect measures something beyond tiredness, especially the low arousal factor does. tiredness doesn't have much influence on that. Now on the between level then, we have the factor 1 and factor 2, and very similar relationships here, very similar coefficients. And that then asks the question, or sort of answers the question, that these two factors are not really different, at least not with respect to the tiredness influence. So that's just like in step 5, where F1b and F2b had similar influence from the time invariant covariates. On slide 41, I turn to the Monte Carlo simulations of cycles that were presented in the paper. The paper gives tables with the simulation results for 3 different kinds of models. We have them listed here: the 2-level random RDSEM, the bivariate 2-level RDSEM, and a cross-classified DSEM. So we have then for the cycles coefficients a random case for the first model, a fixed case for the second, and fixed case for the cross-classified DSEM. And you can think of many more variations with random here, and you can also think of cross-classified RDSEM, putting the cycles on the within level. So many more simulations that can be done. But what's interesting here in general is that each of these cases, each of these Monte Carlo studies uses 2 steps in the Monte Carlo. And that's really representing a general approach that you can use in many other settings as well when you do Monte Carlo studies. So you create some of the variables in step 1 and some of other variables in step 2 using define. And this 2-step approach, the general features of that is described in the user's guide in chapter 12. So let's take a look at the first model then. So it's a 2-level random RDSEM model. So that corresponds to figure 6 of the paper, not this Webtalk, but in the paper. So it has random effects, random coefficients for the cycles variables. And let's take a look at the details here. Monte Carlo names equals PA for positive affect, and this is the variable we want to generate. But then we also generate SX1 and SX2. And what are they? Well, they are the names for the random coefficients for x1 and x2. So random slopes, S as in slopes. Now we're going to work with 500 replications, and the cluster sizes are 256, which means 200 people and 56 time points. So corresponding to the data that we have looked at here in the Webtalk. Cluster sizes, number of different cluster sizes is 1, 56 for everyone. We have a lagged variable, and we want to save all of these 500 replications, the data sets that we generate in this fashion here. We have this star asterisk feature to represent that we do 500 of these data sets. And we're going to declare SX1 and SX2 as between level variables. And the question is, how do we generate them? Well, let's take a look at it. We do a 2-level analysis using base. And here we set B iterations to 200. You could do FB iterations also if you wanted instead. Which signifies that we don't need complete convergence here. It would take a while to do the complete convergence for all 500 data sets, although that could be an interesting run as well. But we only need to generate the data, so we don't need to have perfect estimates. It's the data set that we're after. So then let's look at the model population here then. Here we specify hat variables, so residual variables. So we're looking at the residual relationships for PA over time. And the values, by the way, here in the right column come from one of the real data runs. And you have a residual variance here as well. That's obviously not the full model, but that's what we're going to do in step 1. And then on between, we're going to work with the between part of PA. So that's the random intercept. And we're going to let it correlate with the random coefficients. And the random coefficients are allowed to correlate among themselves as well. And then we give them means for these coefficients, the mean of the random intercept and the two slopes. And then we give variances here as well. So what we're doing here is generating, according to this model, every variable that is not time related. The time-related variables come in step 2. So now we get to step 2, and again, the general features of a second step Monte Carlo run are given in the user's guide, chapter 12. So the data then is given like this. We have the file that was generated in step 1, and we specify that the data type is Monte Carlo, so we have a whole set of 500 data sets to go through. We're going to do 500 analyses. So the names list now, that comes from the order of the variables is presented at the end, at the bottom of the step 1 run. So you have the SX1 and SX2 variables. So these are variables now, varying on the between level. And you have the PA variable, and more importantly, you have the time variable here. A time variable gets saved from step 1, ranging from 1, 2, and up. So then you have, as use variables, PA, X1, and X2. Cluster equals ID, lag 1, and we have the cycles on the within level, as we usually do in 2-level analysis. So that time variable then comes back into play in the define statement for X1 and X2. Time sits here. And now we create the real PA variable, the full PA variable. In step 1, we only generated the residual PA variable through the hat statement. And it was read in up here in the name statement rather. Here are the random coefficients that vary across individuals, multiplying X1 and X2. So that's where you see that you have random coefficients. It's not fixed values, but actually a variable. And in the other examples, we're going to see that they are replaced by values, actual coefficient values. So then you do a 2-level random run. And here now you have a more substantial number of base iterations. And then we have the model here. So here now you specify random slopes for PA on X1 and PA on X2. We use the same name as in the data set here, but these are not the read in variables. These are coefficients, random coefficients that the analysis are going to determine. Then here is the PA on PA ampersand 1, sorry, hat 1. So that's the residual relationship. So these two lines in the model statement are the same as in step 1. So PA has been generated with these values. And then come all the between values here that are also from the same as in step 1, so that we are giving the true values in the Monte Carlo to which estimates will be compared. And the true values are those that we gave in step 1. Step 2 is sometimes called the external Monte Carlo step. So here you have it. That's the 2 steps of the 2-level random DSEM. Let's turn to the second model. Slide 44. So we have a bivariate 2-level DSEM, and here we don't have random coefficients. So this is like our Prologue model on slide 5, but with fixed coefficients. So let's take a look at step 1. We have the same setting with 200 people, 56 time points. Now we bring in a second variable, tired, and that's lag 1. Should be a parenthesis instead of that 1. And we do the rep save, and once again we don't ask for complete convergence. Model population, here are the residual relationships that we generate, and here are the values for the variances, and then the between model where covariances, means, and variances are given. And as always, we'd like to have the same model as model population, so I don't repeat that. So then step 2. So once again, then in step 2, we read in the data set that was generated in step 1, type equals Monte Carlo. And here we have then, once again, the names list with the variables plus a time variable that's been generated. And we're going to use these variables, PA, tired, and the sine cosine variables that we create in the run here. So in define, you have the usual x1, x2 with time coming from the names list up there. And here, PA, the full PA, the residual of PA that we generated in step 1, and then the fixed coefficients, no longer a variable, multiplying x1 and x2. And those values are taken from a real data run. Similarly, tired has fixed coefficients taken from a real data run, and adding the tired residual. So that's how you can compose the full model that you're interested in, the full variables that you want to generate and analyze. So then analyzing them, we have the model. We have here PA on x1. That value is the same as what we used to create it. So we know what the population value is. And same thing for x2. Here we have the autoregression for the same variable, the residual, and here is that key residual relationship, which was specified also on in step 1, etc. Nothing new then really here in step 2. So let's look at the final model, the third model. So now we're looking at a cross-classified DSEM model. So that's the model on slide 11 in this Webtalk, with the cycles on the between time level. So we're looking at the fixed coefficient case. So we aspire only to generate a y variable here, a single variable. And in cross-classified DSEM, we set up the cluster sizes a little bit differently, but you recognize the 200 people, 56 time points, and then you put a 1 in parentheses here, and number of cluster sizes you write like this. I'm not going to go into those details, but this does the job for me here. 200 subjects, that's level 2B in the cross-classified language, and time points is level 2A in the cross-classified language. And we're going to do saving of all of those data sets that we generate, all of those 500 replications, and we do cross-classified analysis, and this is the same as before, and we do a regression here, y on y ampersand 1 on the within level, and on the between level we have the 2a, that's between time, so that's giving that variance here, and between 2b is between individuals. So note here then that the general notation for between time is level 2a, and that's what we need to use in Monte Carlo. We cannot have some other name. And between individuals, between ID is level 2b. So level 2a and level 2b should be stated here. On slide 47 then we have step 2, where we pick up the data, and now we have not only y but also time and some other variables, the ID and the lag1, which we ignore. So we have use variables y, x1 and x2, where x1 and x2 are created here, and we have two cluster variables, ID and time, and the between statement says that x1 and x2 are variables on the between time variable, and we generate x1 and x2 with that time variable. So time here is the same as time here is the same as time here, and we generate y as the fixed coefficients times x1 and x2 plus the residual y that we generated in step 1. So this is a cross-classified analysis, and we specify then the within model, the between ID model, and the between time model. And note here then that ID, this ID is the ID up here, and time is the time up here. So this step 2 is very much like a real data run in that sense. And that's why we can also use define in step 2. We can't use define in step 1. So here then on the between time level you have the cycles on the between time level. This is the residual variance, and here you have the fixed coefficients sitting here, which were created over here. So that's how they were done, these analyses, and again they represent a general strategy for dealing with Monte Carlo studies. You have more flexibility in the Monte Carlo studies if you take a two-step approach. And that's it for Webtalk 7.